This is day 5, and this is the first video. In this video, we're going to learn the basics of regression, and we'll start here with example 1. In example 1, we've been given some actual data where we input the number of hours that have passed since some peaches have been brought into a processing area, and it outputs the number of peaches that remain in the processing area in thousands. We are going to first plot this data set in Excel, take a look at it, and identify what type of function that we think it is. So I've opened up Excel and I've put the data in there. One of the things I do when I create models is I clearly differentiate between the actual original data, so I've labeled this with actual, versus the model data points. I like to label clearly that this is the actual original data versus the data points that we will get soon from the model we're going to create. So I've used the word actual here in my data set labels. All right, so first thing we're going to do in order to create a graph and a model for this is I'm going to highlight the data set. I actually include the labels for the table as well. We're going to go to the Insert tab, and on your Insert tab, you have an area here for charts, a grouping of charts, and you see there's a little picture here for what looks like a little scatter plot, little dots plotted. If you click on that, I'm going to select just the general scatter plot, so it plots the points. And there is my scatter plot for this. You see over 0 up 45, over 0.25 up 38 as given in the data. So I'm now going to just look at this and ask myself what type of function that it seems to resemble. And it seems to me that this looks very much like a line. In fact, it looks so much like a line, it makes me suspect it might actually be exactly a line. If it were exactly a line, then it should be the case that it has a constant rate of change, a constant slope. So what I'm going to do is I'm going to create a quick formula to calculate the slope between each point, each successive point in my table. So here in cell C3, remember slope is change in y divided by change in x. So in parentheses, I'm going to have it calculate the change in y. So this cell here, B3, minus this cell here. That's y2 minus y1 in parentheses, divided by x2 minus x1 in parentheses. So this cell is going to take y2 minus y1 divided by x2 minus x1 and calculate the slope. Now I'm going to drag that formula down and just have it continue to calculate the slope between each successive point. Now I see here now, no, the slope is not constant. It's not negative 28 every single time, but it looks pretty close to constant. It's hanging around that value pretty closely. It's not exactly right though, but when you look at the graph, you can see it's almost a line. And I think if we were to find a straight line that is very close to those points, that line might serve as a good model to help us make predictions about the number of peaches in the future. So my goal here is to find a straight line that's very close to these points. It's called a best fit line. All right, we'll find the equation of a line that's a best fit to meet these points. It won't go through them exactly because it's not a straight line, but it'll be close. We're going to use Excel's regression abilities to do this. In order to do this, pick one of these points and click on it with left click. You notice when you click on one, it highlights all the points. I then right click, and you notice one of the options is Add Trend Line. So I click Add Trend Line. And now an option menu comes up over here. Now, when you create a trend line, you need to understand the type of function that you think would be the best fit. And you're going to select that option over here. Now, Excel will calculate any type of function that will be a best fit for these. So it will pick any type of function that you tell it to. So for example, I could wrongly think this looks like an exponential function. So if I clicked exponential, it's going to find the exponential function that best fits those points. But notice that exponential function would be concave up, and that doesn't make sense for this set of data. This set of data doesn't look concave up. Excel will give you that, but that doesn't mean it's the thing you should select. You should select the function that makes the most sense for the data you're given, and in this case, linear, because it looks almost like a straight line. So I select linear. I'm going to bring down the menu bar. At the bottom, you should see an option for display equation on chart. So I select that, and you notice then it adds in the actual equation of that best fit line that it created. All right, I'm going to go back to my graph now. Lastly, I always click on the actual equation here. In general, it's a good idea to have a lot more accuracy in the parameters of this best fit equation. In general, we're going to get parameters, coefficients, that have decimal place accuracy that goes out a long, long ways. So in general, you should click on the equation, come on over here to the menu, and select number. And I, in general, prefer to have a lot of decimal place accuracy for the parameters in my equation. So I select number under category and I take it out to 11 decimal places of accuracy. I also uncheck this box so that it doesn't throw commas in the middle of each of those numbers. So look at that. It changed the coefficients so that they're showing out to 11 decimal places. Now in this particular equation, it didn't have that much accuracy in the equation it gave us. They're all just zeros. But in the future, this is going to be very important that we get a lot of accuracy in our coefficients. All right, so we have created an equation y equals negative 28x plus 45.2, and that model is a good predictor, a good model for this data set. Now what I'm going to do is in Excel, I'm going to kind of recreate this table on this time frame, but I'm going to do it using this model, this equation, and the values that I get should be pretty similar to the original values. They won't be exactly the same, right, because it doesn't go through those points exactly, but they'll be close. Okay, so here I've just written in the new table that I'm going to create. It looks just like the table above, except you'll notice that my output values are now going to be based on the model, the equation of the regression line that Excel created for us. And I'm still going to just plug in the same input values so that we can compare them and see. So here in cell B12, this cell should equal negative 28 times x, where I get the x value from the cell to the left, plus 45.2. So I'm using this equation to create the output value, pressing enter. All right, and I'm going to drag that formula down, and just look if you see a little comparison here. The actual data told us that at time zero there were 45,000 peaches. According to the model, at time zero there were 45,200 peaches. That's pretty close. And again, similarly, after 1 hour, in the actual data there was 17,000 peaches, but in the model it says after 1 hour there was 17,200. They're all very close to the model. But the useful thing about having a model is that now I can make predictions about the future. I can extrapolate. I could, for example, go up to 1.5 hours in the future, drag that formula down, and it tells us after 1.5 hours you can expect to have 3,200 peaches. I could also interpolate, meaning I could plug in time values in between 0 and 1 hour, in between the beginning and end of the given data set, for example, at 0.3 hours. After zero point 0.3 hours, we should expect about 36,800 peaches. That wasn't given in the original data, but it's a really good estimate of what we would expect. So coming back to the original problem, it asked us to plot it, find a best fit function. So I'm saying after plotting the points, we see the data is very close to having a linear shape. It's almost straight and it's decreasing. We are going to use a linear function as the best fit model. So using Excel, we found, remember our equation was y equals negative 28x plus 45.2. So I'm going to go ahead and define that using the letter T for time and P of T for peaches. So it's P of T equals negative 28T plus 45.2. T represents the number of hours after the peaches were brought into the processing area. P of T is the number of peaches remaining in thousands. Notice when I write out my model, when I answer the question, I don't just include the equation, I also include a clear explanation of the meaning of both variables. So here's my equation where T means this and P of T means this. Every time you find an equation or use a model, you need to clearly identify the meaning of both variables. Next, it asks us to graph our model from time 0 to time 1.5. So back into Excel here, the first thing we do when we create a graph is we create an input-output table on that time frame. So it asks us to create it from 0 to 1.5. So I've created a table from 0 to 1.5. You can select how many points you want it to plot in between. So I have these here. These will be fine. I then highlight them, go to the Insert tab. This time I'm going to create a smooth line graph. Instead of this scatter plot where it just plots the points, if you select this smooth line graph, then it just draws the line. Let me push that down a little. Now you can select the graph, right click, copy and paste that right into a Word file, like so. So you can have a nice pretty picture right here in the middle of your Word file. Mine's not very well labeled. I probably should have put some labels on the input and output axis, but you can do that when you're creating projects and such. Part C asks us to use the model to identify the number of peaches in the processing area after 0.6 hours. So back in Excel, it's asking me to use my model to plug in 0.6 hours. You can simply go to the table and replace one of these values with 0.6. So I'm going to take 0.75 out and put in 0.6 for hours. Press enter, and the function calculates it to be 28.4. Okay, so this means P of 0.6 equals 28.4. And a complete sentence to explain the meaning. After 0.6 hours, there's 28,400 peaches remaining in the processing area. It asks us to use the model to identify the amount of time until there are 35,000 peaches. So again, back to this, I have my model table here where we have the formula of our model in the column B, and I want it to find when the output is 35. So it looks to me like it's going to occur here somewhere between 0.3 hours and 0.6 hours to have Excel identify when the model outputs 35, we need to use solver. So I put my cursor, I'm going to put it right here in cell B14. I go to data, solver. So I click on solver. It says I want objective cell B14 to change to a value of 35 by changing the X value cell. So cell A14. Change cell B14 to a value of 35 by changing the X value cell. I press solve. It changes it, solves it for me. It says, all right, it equals 35 when you input a value of 0.364286. So I'm going to say about 0.36. So in other words, after 0.36 hours, there will be 35,000 peaches. Lastly, it asks us to write a complete sentence to interpret the meaning of the slope. So the slope in this problem is negative 28. Now, I recommend that you get in the habit of writing a slope as a fraction, right? A slope is a change in y divided by a change in x. So in this case, it's negative 28 over 1. Then it's helpful to add units to the numerator and units to the denominator. Again, the numerator is the change in y, the change in output. So in this problem, the output is the peaches in thousands. So the numerator is negative 28,000 peaches. It goes down 28,000 peaches. The denominator is inputting hours, so it increases 1 hour. And when you interpret a slope, you're talking about a rate of change, how the function is changing. It's saying every hour the number of peaches decreases by 28,000.